on the Future Circular Collider at CERN. So please, the stage is yours.
Great, thank you very much, Catherine. Let me see if I can share my slides. Can you hear me well?
Yes, we hear you well.
Okay, very good. So hopefully you can see my slides, and I'll put it on. Okay, yep, all good. So indeed, it's a pleasure to be with you, even though I cannot be there in person on this particular occasion. But I'm happy to report on the Future Circular Collider and also the feasibility study in particular, which has been launched recently in terms of that project. So what I want to refer to is, is the fact that we've had, as many of you know and participated actually, can someone please mute? Someone has their mic open, I can hear an echo. Can everyone? Yeah, that's better, thank you. Yeah, okay. So this actually refers to the update of, no, that's not good. I think everyone has to mute, otherwise I'll get an echo. Hello? Yeah, okay, that's better. Thank you. What I was referring to is the scientific priorities for CERN for the future are actually set out in the update of the European Strategy for Particle Physics, which was updated just over a year ago now in June 2020. And of course, part of that European strategy, which develops a roadmap for European particle physics well into the future, is of course the LHC and its high luminosity upgrade. And those two elements are now in either in operation mode or in preparation mode. From the mid-2020s, we will also have the high luminosity LHC, and there has been a dedicated presentation on that in this workshop. But looking further ahead, the European strategy has underlined the importance of a Higgs factory for the further understanding of the Higgs boson itself, and that could be done by various means, either in a circular collider mode, of which the FCC is a prime candidate for such a facility, or a linear collider mode, and that's where we have the International Linear Collider and CLIC offering the two possibilities for that sort of scheme. In addition, and in parallel, I would say, the European strategy has set forth a program of investigation for the technical and financial feasibility of a future high-energy frontier machine in a 100-kilometer collider at CERN. And I'll be focusing both on that longer-term machine, Hadron machine, and also on the Higgs factory related to the FCC in this presentation. All these future projects, of course, need R&D, accelerator R&D, and also detector R&D. And although I don't have much time to talk about that, there is in progress now both an accelerator R&D roadmap and a detector R&D roadmap process, which is going to be delivered to the CERN Council towards the end of this year, which actually implements or sets out a roadmap for implementation of the strategy of the European Strategy of Particle Physics of last year. So that's in progress. So what I'll be talking about in this presentation is this Future Circular Collider, which you can see there in relation to the LHC hosted by CERN in the Geneva area, straddling, of course, the French and Swiss border in the region of Geneva. So, so what is this? The Future Circular Collider itself, the study was launched, the phase 1 of that study was launched in 2014, and it underlined an international FCC collaboration to host at CERN a new facility, a research infrastructure, a unique facility in the world based on a proton-proton machine, which is called the FCC-HH, which actually will define the infrastructure requirements for such a facility, based around a tunnel, which will be somewhere in the range between 80 and 100 kilometers in circumference, and this will define the infrastructure in the Geneva area. This Hadron machine, the R&D, as I'll come back to later, is very much focused on the requirements of high field magnets, superconducting magnets, reaching up to 16 Tesla in magnetic field to be able to reach 100 TeV proton-proton collisions at the center of mass energies. As a first step, and leading towards this future Hadron-Hadron Collider will be an E+E- collider, the FCC-EE, which will be for the purposes of a Higgs factory and electroweak factory for that matter. In addition, as part of this study, this phase 1 study, there was the option of a proton-electron collider, the FCC-HE option, which was studied, and also perhaps a high-energy LHC machine, which will be the LHC housing center of mass energies up to about 27 TeV with the 16 Tesla superconducting magnets foreseen for the PP collider for the FCC. So that is the reference, which was set out already about 7 years ago in 2014, and I will discuss what's happened in the intervening period. So the FCC program itself is inspired by the very successful LEP and LHC programs at CERN, and this tandem of operating lepton machine and a hadron machine has served the particle physics community very well, and also serves CERN very well. And indeed, in terms of the FCC, this foresees a comprehensive and cost-effective program maximizing the physics opportunities based on the stage 1 FCC-EE, which will be the study of the Higgs boson itself, the discovered Higgs boson, and perhaps others to come in electroweak and the top factory at the highest luminosities. So this is effectively a Higgs and electroweak factory of study. Followed by stage 2, Hadron-Hadron machine at the top colliding energy of 100 TeV as a natural continuation of the energy frontier, with also the ion and electron hadron options in the background. So this actually involves a complementary physics. It involves a common civil engineering, which is very useful, and common technical infrastructures, at least for the most part. And we are building on and reusing not only CERN's existing technical infrastructure, but also the expertise available in the lab, which has been developed over many decades. So this will offer the possibility of an integrated project, which will provide a seamless continuation of high energy physics beyond the high luminosity LHC. And these are the two options, which I'll come back to in a minute, of the two house in the same tunnel, which is extremely cost effective, of course, both the electron positron and the Hadron machine that would follow it subsequently. So just a couple of slides on the physics. We've had a very nice summary by Patrick Janot recently, which shows for the FCC-EE option, the motivation for such a machine is really to produce in abundance at very high statistics the particles of interest here, the production at the Z peak, production at the WW threshold, at the HZ threshold, and also at the TT bar threshold at 350 GeV. So you can see here the range of energies is quite unique. Very nice energy range for standard model heavy particles at the highest luminosities, and not only that, but you get a very precise center of mass energies known to a very high precision at the KV at the low energies and at the MeV range at the higher energies. And very importantly, you can see here at the various scanning points, you see the very high production rates of the particles of the Higgs boson and also of the electroweak particles. And that is in relation to what the CEPC offers in terms of luminosity as a function of center of mass energy, and also the possibilities offered by the two linear collider options shown here in blue, the ILC, and also CLIC here in green. And looking forward, to the subsequent Hadron option, the advantage here is, of course, the tremendously high integrated luminosity, which can be gathered in about 20 years of operation at record energies of 100 TeV. This estimate of 30 inverse attobarns is about a factor of 10 more than what will accumulate in the LHC and high luminosity LHC option. So, and of course, this translates into a very high production rate of the known particles, the known Higgs particles and electroweak particles, but also allows to perform high precision studies of the Higgs and top, and sensitivity to heavy new physics, all the way up to several tens of TeV, depending on the particle you're looking for, whether that's new gauge bosons or new particles of dark matter, which can reach up to several TeV in reach. So new windows, new vistas open, both in terms of the statistics and precision offered by the FCC-EE, and also the precision and mass range available to a new FCC-HH machine. So these are very important and very key underlying physics motivation themes, which motivate the machine FCC-EE and FCC-HH. So moving on now to the machines itself, we have the FCC-EE basic design choice, which is shown here on the right. And this is actually a double ring electron-positron collider, the two rings shown here in red and in blue in counter-rotating form. This will have a common footprint as the Hadron machine, except the details around the two interaction points. At the moment, we are expecting to have 2 interaction points. The current design includes 2 interaction points, although, of course, the physics may warrant more than 2, and as we had in the case of LEP, perhaps 4. And that's a design option which will be studied if such a requirement is needed. Of course, building 4 very large experiments requires the resources to do that, and also the community to be able to put together 4 large experiments at the FCC-EE. But that's something which we can look at. What is also very important is that there is a booster synchrotron, you can see here in green, which is inside the tunnel as well. And this is provides the top-up injection scheme for high luminosity operation because of the significant losses due to synchrotron radiation of the electron-positron beams circulating in the machine, and I'll come back to that later. So this requires a third, I would say, a third accelerator to boost the intensity of the main collider in terms of a top-up energy scheme, which has been used also in the past elsewhere. And this will be a new application of such a new device. And you can see here around the interaction point G, for example, you see the functions, the beta functions of the electron beam and the positron beam coming together at a relatively high collision crossing angle of 30 milliradians. So these are quite large horizontal crossing angles, which will be offered by a Crab waist collision optics, which I'll come back to in a minute as well, and which we are incorporating actually in the in the high luminosity LHC. So the collider parameters, as I mentioned earlier, there are various, there will be a scan of beam energies from the Z peak all the way to the TT bar threshold at 182.5. This is certainly an ampere level machine, and you can see here the beam current at the Z peak is 1.3 amps, and it decreases as we go to the higher energies. Number of bunches very high at the Z peak. The other thing of note is, of course, the synchrotron radiation loss per turn. At the TD bar peak, we lose about 9 GeV out of the 182 GeV available. Hence, the requirement for this top-up injection through the booster scheme that we have. Another interesting point is that another key parameter, figure of merit of such a machine, is the luminosity per the interaction point. And here you can see tremendous luminosities of about 2.3 10 to the 36 at the Z peak, and about 1.5 10 to the 34 at the TT bar threshold. So these luminosities, together with the high intensities and the small beta functions at the crossing, offer the possibility of attaining these very high statistics as required by the physics. So the design concept itself, we don't start from scratch. Obviously, there's a lot of lessons and techniques which have been learned from past colliders, from past E+ minus colliders. In addition, of course, to LEP, there is the B factories, the current one, the SuperCake B, which is shown here. There's Daphne for crab waste. As I said, the SuperCake B factory, which is now operating at KK Lab in Japan. And I'll show you in a minute that coming to a very small beta star at the interaction point, which offers the high luminosities through also crab waste interaction collision. The LEP, which we learned how to operate such a machine at record energies, and the synchrotron radiation effects, and also other E+ minus colliders around the world. I should also underline the top-up injection at KK, which was the first of its type, actually, operated at those B factories. So this knowledge and techniques that have been learned over the past years, combining these successful ingredients over several last colliders, will offer us the knowledge to attain these high luminosities reaching up to 10 to the 36 at the Z peak, and the very high energies of about 382.5 GeV beam energies for the TT bar threshold. Moving on, this is because we will be scanning various energies from the Z peak to TT bar. We go from an ampere class facility at the lower energies, as I said, 1.3 amperes, all the way up to a high gradient machine where we have a very high radio frequency voltage of about more than 10 gigavolts. So this is a unique machine offering not only ampere class machine, but also high gradient machine in a circular mode. So when we do operate such a machine at various energies, we would have to do changes, of course, to the radio frequency system so that we can satisfy these different requirements for the RF, and hence there will be shutdowns between the various operating modes of the accelerator in order to upgrade the RF system. And that is one of the requirements, one of the specialties of such a staging scenario of moving on the scanning peak for the various energies. The figures of merit, I'd just like to mention one of them in terms of the luminosity versus the electricity consumption. I think from the outset, we have to be very careful that we build a machine which is very sustainable and environmentally friendly. And I think these concepts are embedded in right from the reference of such a machine to ensure that we do satisfy environmental and sustainability requirements as required by society, I would say, in addition to what we need in terms of our machines. So one of the figures of merit is this luminosity over the warp plug power in terms of the luminosity 10 to the 32 per square centimeter per second per megawatt in warp plug power. So you can see here, as a function of the center of mass energy, we have for two collision points a very favorable L/P ratio, and we want to maximize that all the way up to the TT bar threshold, after which certainly ILC and the click facility take over at the higher energies, And then I also show the muon collider, muon accelerate collider option, which has been discussed recently, and perhaps also at this workshop. So this is it shows the advantage in terms of the energy consumption. For just such a machine, we have a very nice L/P ratio, which works in the favor of both of the requirements for the physics, but also for expectations from society in building such a sustainable machine. Moving on, this shows as one about the latest, I would say, examples of where we are learning a lot from is another Eplasti machine, and that is SuperCake-B in Japan. This is a double ring electron-positron collider, has a B factor, an asymmetric B factor in energy, which has a design energy of 8 × 10⁵, and a beta star of about 0.3 millimeters. And this 0.3 millimeters is the design study, and they have actually reached just recently, a few months ago, a world record of 0.8 millimeters. And this beta star of 0.8 millimeters, which has been achieved in both rings at SuperCake-B, is going to be a very, very important element of what we will implement at the FCCEE in order to improve that luminosity as required. So this is very much a very nice example of work which is going on now in other physics laboratories, which will be serve as a basis of which we'll build on for the FCCEE. Another potential interesting collaboration is that between the electron-ion collider, which is has just recently been approved to be built in the US at Brookhaven. You can see a lot of similarities here between the electron-ion collider and the FCCEE, and here I'll show you the values required at the Z peak. And we have launched in terms of beam current, in terms of bunch spacing, in terms of bunch population, in terms of beam energy. There are a lot of similarities there, in addition to the array frequency and other technical elements. So we have launched a discussion with the EIC teams to see, to identify the synergies and how to collaborate to develop the equipment common in some sort of common collaboration, which can be used in both facilities, both in the US site and also in the FCC at CERN. Moving on, the technology is quite conventional, I would say, in terms of magnets. These are prototypes of low power, both dipole magnets here, which you can see on the left. And this is a prototype which has been built, and a twin focusing defocusing art quadrupole, which has been designed and actually prototyped here with copper conductor. So these are rather conventional magnets. At the moment, the design of the FCCE considers such magnets, and we are in the process of prototyping them. So that's already a very good step forward in terms of developing the magnet, which will be one of the two important elements building up this machine. So that's already good progress. Moving to the HH facility, this is, of course, in the same tunnel, in the same 100-kilometer tunnel also. In this case, however, there will be a single ring, which will be based on the dual aperture superconducting magnets, very similar to what we have in terms of the LHC and high luminosity LHC. There will be, at the moment, the current design foresees two high luminosity experiments situated at positions A and G opposite, very similar to Atlas and CMS, although we might have another two experimental sites, L and B, which could house dedicated experiments combined with the injection scheme, very similar to where Alice and LHCb are in terms of the LHC. Collimation points, extraction, dump, RF insertion, and the injection itself, there are two options being considered. One is to use the LHC itself, an upgraded LHC while operating at 3 TeV, in beam energy to inject into the FCC-HH, or an upgraded superconducting SPS injecting at 1.2 TeV into the FCC. So these are options which are under study, and also alternative layouts are also under study, particularly if we will be going towards 4 experimental sites rather than the 2 which have come out of the phase 1 design of the FCC-HH. The main collider parameters for the stage 2 PP machine are the very high record energies of 100 TeV collision energies compared to the design values for LHC and high luminosity LHC. The requirement here is, of course, the development and the availability of dipole magnetic fields of 16 Tesla. We're not there yet, although great strides have been made progressively approaching that 16 Tesla magnetic field in accelerator grade magnets. The other point I'd like to mention is the synchrotron radiation itself. Although it's not an issue at the LHC, we're looking at about 2.4 GeV radiation per ring radiated away through synchrotron radiation. So this is something which we have to take into account. The beta star is it's similar to what we have at the LHC, and the luminosity will be hopefully operating at a factor of 10 or so higher than what we'll have at the high luminosity LHC, and hence we will be able to attain integrated luminosities which is significantly higher than what we have in the high luminosity LHC. The other interesting element, and I think this is a point of challenge, I would say, is to be able to protect the machine against 8.4 gigajoules of stored energy in the beams itself. So that's a factor of 10 higher than what we'll have in the high luminosity LHC. So this shows what are the challenges. Of course, this is a plot of the peak luminosity at various Hadron colliders in the past, of which there's only been 5, starting from the ISR at CERN in the 1970s, followed by the SPS collider, again at CERN, RIC at Brookhaven, Tevatron at Fermilab, LHC, and the future FCC-HH option. So the step to be taken between the LHC and the FCC in terms on this plot of peak luminosity over as a function of center mass energy is as the same as the step we took going from the Tevatron to the LHC in terms of luminosity and energy. So and as I said, the key technology here is, of course, the development of these high field magnets. And this is the key feature of the accelerated R&D, one of the key features of the accelerated R&D program of implementation of the European strategy. The key element there is high field magnets for the FCC-HH. So moving on, you can see there is now a launched worldwide FCC niobium 3tin program, where we do not depend on niobium titanium as we have done for the FCC, which has enabled us to run the LHC at 8.3 Tesla. We will be operating at 16 Tesla, and hence we require a new type of conductor. And this conductor, the main development goal is to develop a conductor performance increase of about 50% relative to the high luminosity LHC. And this, we need the current density of about 1500 amperes per square millimeter, which will enable us to increase the density, the current density, which will enable us to reduce also the size of these dipole magnets. So indeed, over the past few years, we are working together, not only with universities and institutes, but also with industry. As you can see here, this is a worldwide collaboration, which will enable us to develop the new type of conductor based on niobium 3tin, which already shows very nice results going out to about 15 Tesla also. And I'll show you one very nice example. Well, first of all, I'll show you the 16 Tesla design activities and options. These are 5 different types of magnets, which are developed by 4 different universities or institutes around the world. And we are to build, based on these designs, short model magnets of about 1.5 meters in length by the mid-2020s. That's one of the challenges which has been launched as part of this feasibility study of the FCC. And in this work is being done in Europe mostly. However, on the other side of the Atlantic, there is a very important US magnet development program, which is underway, particularly at LBNL and also at Fermilab, which are developing the same type of R&D programs for high field magnets. And indeed, the US Magnet Development Program has produced a short model, as you can see there, about 1.5 to 2 meters, which actually reached 14.5 Tesla based on the new conductor of niobium-3 tin. And this is, you can see here, the Bohr field as a function of the quench number. After a certain number of trainings, of quenches, they reached 14.5 at 1.9 Kelvin, which is the superfluid helium temperatures offered. So that's a fantastic achievement, and this bodes very well for the development of these magnets for the future. So we have a program until 2027, which is the time of the next European strategy roadmap, starting from where we are today and building the first type of niobium-3 tin magnets for collider scale production. This will be done for the high luminosity LHC, which is currently underway, and this will demonstrate actually for the first time accelerate in an accelerated environment these new type of machines, these new types of magnets for the high luminosity LHC. In parallel, there is a program of activity, and CERN is very much involved in that, in developing high temperature superconductor. You can well imagine if such high temperature superconductors can be shown to work for accelerated grade magnets. You can either go to higher collision energies for the same ring, or you can reduce the ring size for the same colliding energy. So this is work which is led by Luca Bottura's group at CERN to develop not only the niobium-3 tin magnets, which is the baseline for the FCC-HH, but also to look into new activities based around high temperature superconductor, whether those high temperature superconductors, perhaps operating at 40 Kelvin, or perhaps why not even 70 Kelvin, can replace all the arc magnets, or perhaps only a certain number of them in the arcs, in the short stretch sections particularly, which in any case will reduce the costs of such a machine. So the footprint in the Geneva area, moving away from the magnets, this is now trying to find a footprint of such a machine in the Geneva area is not obvious. The present baseline position was established considering the risks associated with construction, and also the type of rock which exists in the Geneva area. Ideally, we want to drill through and excavate through molasse rock for the tunneling and avoid the limestone with karstic structures, which have water elements in them, just as we had for the LEP LHC tunnel digging around the Jura Mountains, which posed problems both for LEP and also for the LHC. The first stage consisted of 12 surface sites around the Geneva and the Swiss and French border region. Now we're looking at reducing those pit access sites to 8. One of them might be around Annecy, which I'll come back to in a minute, which will possibly require a new laboratory to be built there, just like we built the SPS in France to support the just like we built Prevesan in France to support the SPS activities in the 70s. we might need to build a new laboratory, a new CERN site in the Annecy region, where part of this tunnel will go through. So this shows you the elements. We could have the total construction period would be, this is civil engineering construction period of about 7 years, although the first sectors could be available after 4.5 years, in which we could start installing the technical infrastructure inside that portion of the 100-kilometer tunnel. So that sort of gives the first indication of the timeline required to have access to such a tunnel. So this is the first FCC integrated project technical schedule, which has been produced. Year one here is basically 2021, where we are today. And you can see it extends over 70 years in total. There will be 15 years of operation of the FCC EE machine and 25 years of operation of the FCC HH machine. And the initial period, the coming 18 years, will consist of taking care of all the administrative procedures, both for Switzerland and France. Although 3/4 of the machine will be located on French territory, 1/4 will be on Swiss territory, and doing, of course, all the preparatory studies and work for the civil engineering and actually carrying out the civil engineering itself, and then followed by the FCCEE machine construction and installation and commissioning, and in parallel developing the systems required for the Hadron machine, which will be installed following the construction, the termination of the electron-positron program. So this gives you the overall timelines. The initial period consists of engineering design, energy efficiency, and maintainability. And then we go into the conductors and high field magnet technology required for the Hadron option. So overall, it's an integrated project for 70 years. And if I look back perhaps to the case of LEP/LHC/high luminosity LHC, in terms of years, it's very similar, I would say, in terms of overall years from the early 1980s to the year 2040. It's a little bit longer, but very similar timescales. So this first part of the study was actually documented as part of the conceptual design report in 4 volumes. There is 1 volume on the physics, 1 volume on the electron-positron collider, 1 volume on the Hadron Collider, and another volume on the high energy LHC option. And these have been then they've been published, and you can get access for them of them there. And they're actually fed into the European Strategy for Particle Physics as part of the significant input into that process from the FCC study. So there were more than 1,350 contributors from more than 350 institutes, which really made this into already a very global and international effort. So following that phase 1 of the study, the conceptual study, we have now, following the European strategy roadmap process of last year, we have launched what's called the FCC feasibility study. And this is stage 2 of the work of the FCC. And this actually will address the recommendations of the European Strategy for Particle Physics. And I just highlight here the fact that one of the comments made by the European Strategy for Particle Physics is that Europe, together with its international partners, should investigate the technical and financial feasibility of a future Hadron Collider at CERN with a central mass energy of at least 100 TeV and with an electron-positron Higgs and electroweak factory as a possible first stage. And that's exactly what we're doing. We are implementing that roadmap in terms of the FCC, okay, through this feasibility study. There are many goals of this feasibility study, and I will not go into all of them, but I'll just mention that the main one, one of the main ones is, of course, to look at the placement and layout of the tunnel, where the ring will be situated, looking, of course, at the geological, technical, environmental, and administrative feasibility of building such a tunnel and the surface areas in the Geneva area. Pursuing together with the host states, France and Switzerland, the preparatory administrative processes required for approval of such a project, or optimization of the design of the colliders and the injection chains as well, and supported through a targeted R&D roadmap and activity. And I would say also identification of the substantial resources from outside of CERN's budget to be able to actually realize such a challenging project. So all this, the feasibility study has to report by the time of the next European strategy process, which will be around 2026 or 2027. But as I'll show in a moment, there's quite a few steps to reach that. So this shows a little bit more detail, and this is where support and help is solicited from the worldwide particle physics community. In terms of what has been set up is actually 6 working groups. One is physics experiments and detectors, the other one is accelerators, the other one is technical infrastructure, and then organization and funding, and civil engineering and host state processes. This study support and coordination runs through horizontally these other 5 work packages. So these are the areas which we have to deliver, and this is the timeline which we have to do this, starting from mid-2021. In fact, the feasibility study was launched at the FCC week in June of this year, and the end point is with the delivery of a feasibility study report, which would update the CDRs I mentioned earlier and provide a more technical appraisal and a more technical design of the concepts presented in the CDRs. And at that point, we should be addressing, of course, very substantially the technical and financial feasibility of building such a machine. And of course, this will feed into the next European strategy towards the middle to end of this decade, at which time we would hope a decision will be made on the future of such a machine of the FCC, and a decision by the European strategy, which will then obviously take in international partners. So I will move on to just mention another couple of things which are happening, and that is and acknowledging one of the key elements of being able to carry out this feasibility study is the so-called FCC innovation study, supported by the Horizon 2020 design study for the 5-year period, 2020 to 2024. And this brings in many partners, beneficiaries from Europe, which are participating in this innovation study, and also international partners from around the world. And you can already identify here the DOE in the US is a key partner for the FCC, and very much recognize and acknowledge their kind support for the FCC, and also the same from the Russian Federation, in particular the Butler Institute of Nuclear Physics in the Russian Federation, Novosibirsk. So these are the innovation study, which is being funded by the European Commission to undertake this feasibility study as its main aim and goal for the next years. So what I'd like to maybe move on to is the main part of this feasibility study is actual placement of the collider in the Geneva area. You can see here on the right the Lake of Geneva, and you can see the border between France and Geneva situated there in the dark violet color. And there are various options which have been looked at, and the overall placement and optimization process across both host states, which follows the principle of avoid, reduce, and compensate directive according to the European and French regulatory frameworks. You can well imagine we are building this machine in a residential area, in a built-up area, and you can well imagine all the hurdles which have to be overcome to be able to build such a machine, even though it is situated 100 meters underground, or even more perhaps. Nonetheless, there will be surface sites, there will be surface buildings, and there will be pits leading from the surface sites to the underground ring itself. And this process has started, and this footprint explorer is a new, together with civil engineering firms, we are working together to be able to do this multi-criteria optimization of placing such a tunnel in the built-up area in the Geneva area. So this is a scenario situation which we're building now. And as you can see here, all of the various hurdles, the various constraints, starting from nature, and this is the Jura limestone, which obviously we want to avoid. We have protected areas around the lake. We have densely urbanized areas located in Geneva. You can well imagine there's another mountain range here to the southeast, and another mountain range is here. So we are quite limited in how we can build this machine. The current estimates show that perhaps the best size which fits in this in the surrounding areas is about 92 kilometers in circumference, taking into account all the constraints that you see some of them on this diagram. So now, one of the other elements we are trying to prototype in the next, as part of this feasibility study and as part of this innovation study, and this is being done with international partners, is developing a complete arc half cell mock-up for the FCC-EE. And this includes the girder vacuum system, antechamber and pumps, quadrupoles, sextupoles, dipoles. And this will be hopefully delivered as a prototype by the mid-2020s. One of the other key elements is key beam diagnostics elements. Again, this is being done with international partners, and you can see some of them listed here, which have signed up to this to the FCC collaboration. And this is some of the deliverables by these institutes. Another key set of deliverables is a 400 megahertz superconducting radio frequency cryo module, plus the prototype multi-cell cavities for the FCC-HZ operation mode, positron capture LINAC, and this is done by together with our partners in Switzerland. And here I'd just like to underline the significant contributions and support from Switzerland through Chart 2 program for accelerator technologies and research during this period, which not only includes classic or conventional accelerator equipment, but also support for geology and geodesy activities, which go beyond conventional accelerator work. A high yield positron source and a beam test of a positron source and capture LINAC at the Swiss FEL is another contribution by this Chart program of R&D. The machine detector interface is very tricky, as you can well imagine, for the FCC lepton collider. And there's work being underdone here to integrate a 2 Tesla detector solenoid and a luminosity monitor and compensation and shielding solenoids, all in one very close region. As you can see here, this is the interaction point, and this is 3 meters away from the interaction point. Also, the design of a narrow beam chamber, which will be the central part of the experiment, a 1 centimeter radius central beam pipe chamber there, and also quadrupole final focus Q1. And this has been also work which is being done to integrate into this machine detector interface. So that part is being developed. A formidable challenge, of course, is the detector itself. And here I show you the challenges for the Hadron Collider. The requirements are well beyond those for the high luminosity LHC, and this will be revisited through this feasibility study. So this is requirements there have to do with a much larger longitudinal event boost at the much higher collision beam energies that we have. We have very high, the produced particles will be very highly boosted because of, especially in the high PT final states. We have perhaps up to 1,000 pileup events per crossing, very much higher compared to the LHC and even compared to the high luminosity LHC. We have energetic jets, we have high PT muons, and we have the requirements of significant radiation harness requirements for the electronics, which will be, and the sensors, which will be in the detector. So all this is being carried out as part of a program of what is called PED, which is the Physics Experiment and Detector program of R&D and coordination, which will brings together those three pillars: physics, the experiments, and the detectors, to design this the detectors for the both the Lepton Collider and the Hadron Collider. And I'll just finish off by saying one or two words about the status of the Global FCC Collaboration, where we are today. An increased international effort is a prerequisite for the success of this study and for the project, of course, which we need. The links to the science, to the research and development, and also to high-tech industry are essential to further advance this, this study through the feasibility work which is going on. At the moment, we have 34 countries involved, from where we have 147 institutes and 30 companies contributing to this effort. And of course, we acknowledge the kind support from the European Commission through 2 design studies for the phase 1, which is Eurocircle, and now phase 2, which is the innovation study. So the FCC feasibility study governance was approved by Council in June. That followed, and that was just prior to the FCC week that we had at the end of June, and the first meeting of the FCC Collaboration Board, which is set up very similar to the structures of the LHC experiments, will be having its first meeting later this month. And I'd just like to leave you with the FCC week, which happened at the end of June, which occurred at the end of June of this year, which consisted of 31 sessions and 128 presentations, very close to 700 participants in the meeting, of where you can see here a great majority coming from EU member states and non-EU member states, but a significant contribution and participation from Asia and also North America, as you can see there. And the next FCC week will be held at the end of May, beginning of June of next year, and that will be held in Paris. Obviously, a very important location, venue, as France is one of the 2 host states of a future FCC. And actually, most of the facility, most of the infrastructure itself will be situated on French territory. And certainly we like to see everyone there next year. So in conclusion, we have completed the first phase of the FCC design study, particularly through the Eurocircle support that we have. We have baseline machine designs, performance matching the physics requirements at the time, and this has been documented in 4 CDRs. There is an integrated FCC program which was submitted to the European Strategy Update, which was updated in June 2020, and the request for the feasibility study as a basis for the project decision later this decade was approved, and actually this feasibility study has been launched, and we're in the process of working through the requirements until later this decade to be able to deliver to the European strategy a feasibility report on how well that such a facility can be actually built technically and financially in the Geneva area. And in the longer term, following obviously approval, going through the approval processes which are required, the longer term goal is, of course, to build a world-leading high energy physics infrastructure for the 21st century to push the particle physics precision and energy frontiers far beyond the present limits of the LHC and the high luminosity LHC. And I'd just like to finish by saying that the FCC collaboration is an open collaboration, and we are welcoming new participants and new contributors to this feasibility study phase and to the FCC innovation study phase project that's also been launched for the coming years. And with that, I would like to thank you for your attention, and I would like to end there. Thank you very much.
Thanks a lot.
Yeah.
Thanks a lot for this very comprehensive overview and showing us the future of experimental particle physics. I'm sure there are questions. Yes, please.
Thank you for the very comprehensive talk. I have a comment about the FCC-EE and the possibility of an E- option. As you may know, two electrons have never been collided since 1971 at Stanford, the center of massive energy 1.1 GeV by Richter and others.
Yeah.
And at every E+ E- collider in the 50 years since then, the low-cost E- E- option has been seriously considered, but always rejected as an empty, exotic, uninteresting channel. Now, if the bilepton resonance in same-sign leptons is discovered later this year, the E- option could become a bilepton machine.
Right.
And I wonder whether the CERN planners are aware of the bilepton as a new reason for the first time to retain the E- option.
Right.
In that.
Yeah. Thank you for the question. Indeed, it's very welcome to hear that. In fact, in the first phase, this did not feature in those CDRs, the electron-electron option. But now is a very good time to bring them on the table again, because we've entered a new stage of studies. And I think I will certainly bring that across to the FCC team, which is working on both on the machine and on the physics. And we'll see if we can take that forward to some extent. As you mentioned, a lot will obviously depend on what will come out later this year. But I think it's certainly something we should keep an eye on. And although, to be frank, this has not been studied so far. It did not feature in the, to my recollection, in the CDRs that we put out a couple of years ago. But this is a good moment now to relaunch that discussion, particularly because positron production of positrons are not terribly efficient. And we would certainly need quite significant R&D on the positron source and the positron production scheme in order to guarantee these high luminosities, which are required in the FCC lepton collider. So I think any suggestions like that, which can make life easier for us in that respect, is very welcome.
Am I right in saying that this E- E- option is a very small additional cost, just 1 or 2% on the total cost?
Yeah. Okay. I'll take that forward. Thank you for the suggestion.
And just a follow-up question: if the decision on FCC is possibly made in 2026 or 2027, what is the realistic year when it would start taking data?
Yeah, I think at the moment, what I mentioned in one of my slides is the current program shows that if this year is year 1, and then we'll need 18 years or so to get everything, all the administration done, all the construction done, and the installation of the accelerator. So we're looking at about the year 2040 for the lepton collider to start operations, plus 15 years of operation beyond that. Yeah. So that's the most optimistic timeline, which we have put down on paper today, and which we are working towards. Okay. But that obviously assumes that the feasibility study and technical studies, which are ongoing now, come to a positive conclusion, and the European strategy gives a positive recommendation later this decade. And then, of course, the procedures of approving the project have to go very quickly after that, as we had for the LHC. I recall, and I made that statement, is that the FCC collaboration is going to be based on an international and global effort, just like the LHC was, but to a bigger extent. And I think this is where we are building now. We have launched an FCC Global Collaboration Working Group with the purpose of encouraging participation also from the non-member states, and not only from the member states, associate member states of CERN, but just like in the case of the LHC itself in the mid-1990s, very much we're dependent on the non-member state contributions to that project, particularly from the US, from Russia, and the other countries, Canada, India, which participated, Japan, which participated in ensuring that we had the LHC approved as a one-stage machine. No. Any other questions?
It doesn't seem like we have other questions, so let's thank the speaker again.
Thank you. Enjoy the rest of the workshop, and apologies I'm not able to be there in person to enjoy it with you.
Okay, and then I'm inviting the next speaker to present, which is Alexander Czarnecki on dark matter searches at Eplasti minus colliders.
Yeah, I think so.
The pointer also?
Yeah, and well, the slides, yes, works. So,
Okay.
okay. Good afternoon. My name is Filip Żarnecki from University of Warsaw, and I would like to present result on dark matter searches at future Eplasti minus colliders. Most of results were obtained in a small team listed here, but I will also mention results from ILD and ClickDP collaborations. So first of all, I would like to thank organizers for inviting me here. I was here 2 years ago, and I would say that being here again really returns me a will of life and really a lot of strength and enthusiasm towards doing particle physics after this difficult last year. So, okay, some motivation. We know, well, we are pretty sure that dark matter is there. but we have basically no hints where to look for it. And so it's difficult to look at all possible places with as model independent way as possible. And high energy plus minus machines offer a lot of options for searching for dark matter. And in fact, looking to the Higgs portal is one of the options, and this is where we could focus at Higgs factories, but linear plus minus colliders, which are another options for the future of particle physics, offer two additional frontier, the high energy frontier, which I will focus on today, where we can extend the Higgs factories based on linear accelerator towards TV energy range. And also there is an option to have fixed target experiments based on the spent plus minus beams, which give really very stringent limits, which could give very stringent limits for light dark matter scenarios, for many light dark matter scenarios. You can have a look at my talk given at another conference if you want to know a little bit more details. So what I would like to speak about today is searches based on the so-called monophoton signature, and this is assumed to be the most general way to look for direct dark matter pair production at E plus E minus colliders, because as any hard scattering process in E plus E minus colliders, it has some probability to be accompanied by hard photon emission, and it is not depending on the new physics, because it's just purely quantum electrodynamics which is involved here. So, and the distribution of these hard photons reflects somehow the kinematics and the differential cross section for the dark matter production. So by observing these photons, we can extract information on the BSM scenarios. So this is the type of analysis I would like to tell you today. So first, I will briefly remind you about the colliders and experiments I will talk about. Then I will spend some time discussing the way we simulate monophoton events. And then I will present results. I will briefly mention results, as I said, from ILD and CLIC-DP studies, which are based on the heavy mediator exchange approximation. And then I will go to our results, which assume light mediator exchange. So somehow these results are complementary. Okay, so let us first start from a brief reminder of the experiments, colliders experiments. So we focus on the prospects for International Linear Collider, which was the current design was proposed in 2013 based on superconducting accelerating technology. The baseline is a collider which will start at 250 GeV and then be extended to 500 GeV. There is also an upgrade option to 1 TeV. Both beams at the ILC will be polarized, electrons to about 80% and positrons to 30%, where the possible stronger polarization is also an option. Compact Linear Collider is another linear collider project based at CERN, where the novel concept of two-beam acceleration is used, and this allows to obtain stronger accelerating fields, and then the accelerator can reach up to 3 TeV, although again the staged implementation is assumed starting from Higgs factory at 380 GeV. At CLIC, only electron beam is assumed to be polarized. This is the summary of the running scenarios we consider in our analysis. As we are looking for direct dark matter pair production, we focus on the highest energy stages, so 500 GeV stage at ILC, where about 4 inverse attobarns are assumed to be collected at 4 different polarization combinations, at 3 TeV CLIC with 5 inverse attobarns collected, most of it with negative electron beam polarization, 20% with positive electron beam polarization. Detectors for both projects detector concepts are very similar. They are based on the so-called particle flow concept. This means that we will try to reconstruct every single particle, and you have here an example of event. And this is one of the more complicated events we expect at Eplasti colliders, and still you see it's very clear. And also you can see that the tracks which we measure in the central calorimeter, we can in the central tracking detector, we can easily extrapolate toward inside the calorimeter. This is because of very high granularity of the calorimeters. They really allow us to track particles inside the whole detector, and this also gives us the best possible jet energy resolution, because we just take momentum measurement from the tracking detectors for the charged particles, and also we expect very efficient flavor tagging. And what is important for our analysis, these detectors will be very hermetic. The instrumentation will go up to the smallest angles of the order of few milliradians. So all the missing energy, missing momentum energies, the measurements will be very precise. So this is a summary of the basic requirements, and there is results I will present are based on the ILD detector concept for ILC and click detector concept for click, while there is also another detector concept for ILC considered, but the parameters are very, very similar to, so basically the fast detector simulation description is the same for both studies. Okay, so now let me come to the simulation of monophoton events. It is the proper simulation of and consistent simulation of signal and background is very important in this type of analysis. We want to have a very precise simulation of these hard photons which can be emitted into the detector. The main background to the monophoton emission in dark matter per production processes comes from the background which I call irreducible, even if maybe from the theoretical point of view it's not strictly irreducible, but from the detector point of view it's reducible because we do not see neutrinos. So radiative neutrino per production is the main background to the radiative dark matter per production. And we need to simulate the spectra for these hard photons as well as possible. On the other hand, we also need to have the proper cross-section estimate for the process as a whole. There's also a significant contribution from radiative BABA events, but this is because of the finite detector acceptance and resolution and final reconstruction efficiency, but still the neutrino per production background dominates. So we simulate both background and signal with Wizard, which is a standard tool for Eplasti colliders nowadays. And Wizard provides quite sophisticated description of ISR, taking into account all orders of soft and collinear photons. And this is very important for proper cross-section estimate. But on the other hand, this ISR photons, which are generated from the so-called ISR structure functions, are so-called effective particles. They represent a sum of all emissions, so they should not be considered as physical particles which can be measured in the detector. So this radiation should be allowed only in the region where there is no instrumentation, and all photons which go at higher angles should be simulated on the matrix elements level. But then we have to take care to avoid the double counting. So we developed a special procedure where we divide the phase space with using the two variables Q minus and Q plus. This is how we call them, and these variables correspond to the virtuality of the electron after emission of the real photon or positron, assuming a single photon emission. And you can see the space in Q minus, Q plus here with detector coverage indicated. And so you can see that all photons which are emitted with Q plus or Q minus above, Q plus and Q minus above 1 GeV and energy above 1 GeV can be measured in the detector, but this means we have to simulate them on matrix elements level, and only the remaining space can be simulated with the soft ISR structure function, as we cannot put this constraint into the result generation. We have to do it at the selection level, so reject events where the ISR was emitted in this, I would call hard photon region. So we validated this procedure by comparing wizard predictions with the semi-analytical KKMC Monte Carlo code, and as you can see here on these two plots, both the multiplicity of produced events, produced photons, and the PT of the radiated photons after imposing detector level selection agree really very well between the two simulations. So for more details, you can have a look at our dedicated paper. What is important with this, well, okay, and in our study, we consider the simplified dark matter model, where we consider exchange of dark matter production through mediator exchange with mediator masses ranging from about 100 GeV up to TeV range. And this is an example of cross-section for production of dark matter with 50 GeV mass through exchange of mediator with 300 GeV mass as a function of the collision energy. And we make this study assuming not given couplings, but giving mass and width of the mediator, and assuming given mass of the dark matter particle. Just to limit the number of options, we kept the dark matter particle type as Dirac-Fermion all the time, and the mass fixed to 50 GeV, and we just consider different mediator masses and mediator width and different mediator coupling types, which I will show on the plots. So for this light mediator scenarios, this ISR rejection, as we call it, so this procedure to evaluate double counting is very, very important, because you can see that up to 40% of events can be rejected at ILC, and up to 50% of events at click. So this would mean that if we would not use this procedure, we would overestimate the production cross-section for this monophoton events by almost a factor of 2. So this is really a very important ingredient in this analysis. For a heavy mediator exchange, so if we are above the center of mass energy, this effect is smaller, but it's still of the order of 20 to 30%, so it's still quite sizable. Another effect which we can see on this level is that not all dark, and this is quite obvious, not all dark matter pay production events do have the hard photon visible in the detector. And this is also interesting to notice that for light mediator exchange, probability to have hard photon detected in the detector is higher than for heavy mediator exchange. So for heavy mediator exchange, it's only about 5% of events where we have hard photon measured in the detector, whereas for light mediator exchange, it can be up to 15%. Here, I show it for different widths of the mediator. And you can also see that where the mediator mass coincides with the collision energy, the radiation probability is significantly decreased. Okay, so I have to hurry up a little bit. So now let's come to the results. Just for completeness, I wanted to just flash results earlier results from studies which were made in the heavy mediator approximation at CLIC and ILD. So at CLIC, the procedure which turned out to be most sensitive to dark matter production is looking at the ratio of the photon energy distributions for positive and negative electron beam polarization. So if there is no new physics, you have these red points here, and so it is just predicted by the standard model that the cross-section for neutrino pair production with left-handed electrons is factor of about 9 higher than for right-handed electron beam. And so if there is a mixture of dark matter pair production, then this ratio changes, and you can see here this drop to this blue line. And by changing, but looking where this changes and how much it changes, one can see what is the mass and the cross-section for production of the dark matter particle. And if no deviations are observed, one can extract limits on the dark matter, radiated dark matter per production. From these limits, one can further try to extract limits or expected limits on the dark matter mass and mediator mass. This is shown on this plot for the assumed mediator coupling equal to 1. And if a signal is observed, one could also, from this deviation shown on the previous plot, should be able to extract the dark matter mass with precision of the order of percent. This was a study which was made on the generator level. Much more detailed study was done for ILC, where again we look for events with single photon in the central detector region, where we just require high tracking efficiency to remove to reject electron events. And you can see that before the detector selection cuts, there is a huge background from Baba events. This is this brownish color, and if after the veto in the tracking detectors and in the so-called beam calorimeter, this is basically gone, and we are only left with the background from neutrino, radiative neutrino pair production. And again, this looking at the distribution of these photons allow us to set limits on the mass scale in the EFT formalism, which this mass scale is related to the mediator mass scale. If we assume that couplings are equal 1, this limit is just a limit on the mediator mass. And this is the limit from the combined analysis of all collected data expected up to 20 years for vector mediator couplings, and you see the limits are of the order 3 TeV, whereas this plot shows how sensitive we are to the beam polarization, and that you can see beam polarization improves our sensitivity enormously. So polarization is really very important, and it's only possible at linear Eplasti minus colliders. And this is the comparison of this heavy mediator type limits, and you can see that mass limits which we can get at higher energy Eplasti minus colliders are comparable with limits which are possible in the corresponding scenario as at Hadron colliders. So I would say even CLIC is significantly better than what you could do with at FCCHH. Okay, so let us now come to our analysis, which focused on light mediator exchange, because these two studies assume that the exchange mediator is heavy. But we realize that light mediator scenarios are still not excluded. It is just a question of the coupling. If the mediator coupling to the standard model particles is small, these scenarios are still not excluded. We could go with this mediator mass down to tens of GeVs probably. It only assumes that this standard model width has to be small. So we tried to understand this prospects, and I already described the Wither-Clever simulation. We used Delphi's framework for fast simulation of the detector response, and so the analysis is limited to photons with transverse momenta around above 3 GeV at ILC and 10 GeV at click. And what is also new in this analysis that we do not look at one-dimensional energy spectra of the photon. We look at 2 dimensions. This is the plane of rapidity, and this horizontal variable, which we call ft gamma, is a logarithm of the transverse momenta, but defined in such a way that 0 corresponds to the minimum transverse momenta and 1 to the maximum transverse momenta as allowed at this rapidity from the kinematics. So that gives us a nice square phase space, which is convenient for limit setting. And you can see that for standard model background, it's dominated by high rapidities, low PTs, whereas for signal with exchange of light, relatively light mediator, we see a clear reach here of events corresponding to radiative return, because this is at 500 GeV ILC, and this is the events corresponding to the radiative return to 400 GeV mediator mass. And by comparing these distributions, we can extract limits on the cross-section. These are limits on the cross-section for radiative dark matter per production at ILC and at click. Compared our limits obtained with different polarizations and combined limits. And as it's expected, combined limits are always the best. And also open symbols show the limits without systematic uncertainties and field symbols with systematic uncertainties. And as you can see, systematic uncertainties are quite important for heavy mediator exchange, where you just count events basically, so you just look at the total cross section. But at in our case, where we focus on light mediator exchange, the impact of the systematic uncertainties is significantly smaller, because we just look for the peak in the energy spectra. So it gets a little bit worse if the mediator is very wide, but still systematics I think are under control. Then we still have to correct these limits for the probability of tagging hard photon. This is what I showed a few slides ago. And after correcting, we get limits for the total dark matter production cross-section. So without this word radiative. So this is total production limits. This is already then independent on the phase space in which we collect photons. And you can see that we can get these limits of the order of 10 femtobarns on the light, for the light mediator scenarios, both for ILC and click. This is for vector mediator scenario with different widths, and this is for mediator with 3% width, relative width, but for different coupling structures. And as you can see, these limits are similar. They differ, but these changes are just here in the light mediator scenarios are up to a factor of 2, I would say. And only again, in the region where the mediator mass is close to the center, to the collision energy, these limits are weaker because the radiative processes are suppressed here. And finally, we can translate these limits to the limits on the mediator couplings to the standard model particles. And these limits are of the order of few times 10 to the minus 3 at ILC and 10 to the minus 2 at click. This is for different mediator widths, and this is again for different mediator coupling structures. Again, this variation is not very large, and the limits are quite uniform up to the kinematic reach of the collider, so up to the center of mass energy, collision center of mass energy. Basically, just before I conclude, I just still wanted to show these results where we compare our limits from fast simulation, these are these points, with limits from full simulation study at ILD, assuming heavy mediator exchange. And as you can see, our fast simulation results are in perfect agreement with the full simulation study. So this somehow confirms that our fast simulation approach is a reliable extrapolation of the results to the low mediator mass domain. So let me now conclude. I hope I convinced you that the Eplasti minus colliders offer a lot of possibility to search for dark matter. In particular, the right mediator exchange scenarios seem to be quite interesting, and we have presented expected limits for these processes, which are of the order of 10 femtobarn for total dark matter production cross sections. And these limits, I should also stress, are stringent than those which could be extracted from the observation of standard model decay channels of the light mediator. So thank you very much for your attention.
Many thanks for this very interesting talk. I'm sure there are questions. Online, there's a question. Oh, yes. So, Alexander Rayal, please go ahead and ask your question.
Hello, can you hear me?
Yes, we hear you.
Very good. So, thanks a lot for a very interesting talk. I have just a general question. What's the typical ratio between signal and background, and what is the systematic did you assume for one collider or another? So just for clinical LC, how important it is.
What is the signal to background ratio? I must say I cannot.
Okay,
I don't have the number in my head, but systematics. I have it in my backup slides. You can have a look. This basically was we basically used the systematics which was used in the ILD study, and quite similar systematics was also in the click studies, and we just used the same systematic uncertainties as in the two studies I presented at the beginning, just to be consistent. So we didn't want to propose our own systematic checks. We just used what collaborations assumed.
I see. So it's typically combined systematic of the order of, say, 1%. How realistic it is? And well, in your study, usually the background of a signal of the background is quite small, so the background is quite large. As you mentioned, you are not sure what the ratio was, but what is typical?
I was a little bit looking for Higgs to gamma gamma in at LHC. So we have a huge background, but what you know is that the background is, well, even here it's even much more precisely predicted because it's purely quantum electrodynamics. So you predict this background quite well. And also, you know, this background is smooth. And what you look for a resonant-like structure on this flat background. So that's why you are not so sensitive to the systematics. And that's why I also think these estimates are reliable, because this is not only the question of the ratio. You just look for a resonance. So it's much easier than just comparing, the cross section. If we just count the photons, it might be much harder. But we have clear resonant peak as it's. Okay, I don't have the.
I understand. Well, but what resonant peak you're looking at? Because you're looking at dark matter and production. What resonant you're talking about? So.
Okay, we focused on looking for mediator, assuming dark matter is relatively light.
I see, but if mediator is resonant,
from radiative return to the mediator mass. So this is, this is really a striking signal. So the same way as you get zero turn visible in the photon spectra, you will just get the second peak in the spectra from this mediator.
I see. But if the mediator is heavy, and you can still produce dark matter, but you wouldn't have a resonant peak, right? So, that's a different story, right?
Yeah, okay. We had to limit, well, there are too many parameters to analyze all of them simultaneously. So we limited this analysis at the moment just to scanning the mediator parameters, and we still plan to have a look at how precisely you can extract details of the dark matter particle. So it's what's happening and so on, but it's somehow the plan for the next stage of the analysis.
I see. So in your scenario, you always produce a mediator. That's why you choose the mediator mass below the click threshold. So it's like you always produce it. That's your scenario, right?
No, okay. In the results, you see we extend to up to higher masses. So this is the light mediator region, and then you have this heavy mediator region. So somehow we consider both, but what we present in the light mediator exchange region is what is new, basically.
Okay. Okay. Thank you.
Okay, I think for the sake of time, we have to move on to the next speaker. A big applause to our current speaker.
Thank you.
And I'm inviting the next speaker, which is Deborah Barreros, to talk on neutrino masses from minimal Scotto seesaw mechanism. Okay, the stage is yours.
Thank you. Hello, everyone. Before I start, I'd like to thank the organizers for the opportunity to present my work here at Corfu. My name is Deborah Barreiros, and today I will show you the work I've done in collaboration with Filipe Joaquim, Raul Srivastava, and also José Valle about a fairly simple Scotto seesaw model where CP violation arises spontaneously. Well, as I'm sure you all know, the standard model cannot explain the existence of neutrino masses and also lepton mixing, and also doesn't give us a suitable dark matter candidate. So one has to go beyond the standard model to try to solve these two problems. Some of these solutions include, for instance, the type 1 seesaw mechanism, where neutrino masses are generated by the exchange of very heavy right-handed neutrinos that are added to the standard model. But if we want to include as well dark matter, then we may consider some kind of scottogenic model where neutrino masses are generated radiatively by the exchange of some dark particles. Well, in the particular case of this work, what we did was to consider a model where both these mechanisms contribute to neutrino masses, and we added as well a single discrete symmetry that accommodates neutrino oscillation data, dark matter stability, and also spontaneous CP violation. But the starting point for this work was a model that was proposed back in 2019 by Valle and collaborators, where they associate each of the two neutrino mass scales measured at oscillation experiments with two very different mass generation mechanisms. So in the most simple case, where the lightest neutrino mass is 0, and we are in the normal ordering hierarchy, then the atmospheric mass scale arises at 3 levels from the type 1 seesaw mechanism, while the smaller solar mass scale may arise radiatively through a scottogenic loop. And in order to do that, they added to the standard model a single right-handed neutrino, along with two other dark particles, a scalar doublet eta, and a neutral fermion F. And after they do this, and after they consider as well this dark symmetry, then these are the allowed diagrams for the masses of neutrinos. So as you can see, the dominant contribution will generate the atmospheric neutrino mass scale, and the smaller contribution will generate the solar neutrino mass scale. So at the end, at the effective level, what we have is that the two mechanisms contribute to the final effective neutrino mass matrix. So as you can see, this is a very interesting model, mainly due to its simplicity. But because it predicts one massless neutrino, can accommodate without any kind of problem neutrino oscillation and LFT data, and also give us a viable winged dark matter candidate. However, if we do not constrain somehow this Lagrangian here, we will end up with no predictions for low energy observables. What we did to solve that problem was to consider our Lagrangian to be CP invariant, and because of that, we had to find an alternative source for CP violation. And we did that by introducing this new scalar singlet sigma with a complex VEV. And once we do that, we can then write these couplings of sigma to our neutral fermions, which after spontaneous symmetry breaking give origin to Majorana mass terms for these neutral fermions with complex couplings. So once we write the effective neutrino mass matrix, we see that we get here a phase which will correspond to the relative phase between the complex couplings of these Majorana terms that cannot be taken away. So in principle, CP violation will be transmitted to the leptonic sector, provided, of course, that this phase here is non-trivial and also that our fields couple differently to sigma and sigma conjugate. Also, another thing that we must take into account is that our scalar potential must contain this phase-sensitive term of the type sigma to the fourth, and I will show you why later on in this presentation. So as you can see, the minimal Scotto seesaw model gives a very good template, not only for neutrino masses and dark matter, but also for spontaneous CP violation. But even though we have considered all our couplings to be and masses to be real, we still have lots of high energy parameters when comparing with the low energy observables. So what we did to once again solve this problem was to try to forbid some of the couplings using a discrete abelian symmetry. And in our first attempt, we consider the most simple case where we only have one right-handed neutrino and one dark fermion F. And in that case, any discrete symmetry that we considered would lead immediately to incompatibility with neutrino oscillation data, either because we would get a zero mixing angle or because we would get an extra massless neutrino. So what we did to solve that problem was to add an extra right-handed neutrino, which we call here nu R2. And we found out that the most simple abelian discrete symmetry that leads to maximal constraints in our Yukawa and mass matrices is this Z8 symmetry. Of course, this is not the only charge assignment that we may consider. We may as well interchange the charges of our charge leptons and then get other possible configurations. Okay, once we take this table into account, we can then see what are the contributions to neutrino masses, which are these ones at tree level and these ones at the loop level. As you can see, we had to add an extra scalar singlet with no VEV in order to be able to close this scotogenic loop. So at the end, our goal was met, and we were indeed able to forbid some of our couplings. Notice as well that our charge lepton sector is non-diagonal, and in this particular case, we have a mixing between the electron and the tau flavors, and we are left also with a decoupled muon. This is actually why we call this symmetry as Z8e tau. Of course, that if we interchange these the charges of our leptons, then we would have other decoupled charge leptons, and in those cases, we call the symmetry Z8e mu, and we have a decoupled tau, or Z8 mu tau, and we end up with a decoupled electron. Okay, moving on to the scalar sector, this is our scalar potential. And once we minimize this potential, we get the CP violating solution, which will correspond to the global minimum, of course, as this condition is fulfilled. Notice as well that we have to have this term sigma to the fourth to be in the potential, because otherwise our phase would end up to be trivial. So as long as we have this solution, we will be able to guarantee the presence of spontaneous CP violation. Other conclusions that we may take from this potential is that our Z8 symmetry will be broken down to remnant Z2 symmetry, and this will actually give dark matter stability, because it prevents the neutral dark scalars to mix with the neutral non-dark scalars. So at the end, our dark matter candidates will be either the dark fermion F or the lightest of the mass eigenstates from the mixing between eta and chi. Moving on to the low energy constraints, recall that these were the matrices that we got from our symmetries at 8e tau. And once we plug this information into the effective neutrino mass matrix expression, we get this structure here. And as you can see, we get a 0, which we can test against data. And also notice as well that the presence, the contribution of the scotogenic loop is really crucial in order to ensure the existence of CP violation, because if this term was not here, then we would be able to take this phase away and we would end up with CP conservation. Going to the basis where charge leptons are diagonal by performing this rotation on the effective neutrino mass matrix, we get 3 possible constraints according with the symmetry that we consider. And now we have to test these constraints against data. And for that, we use the data, the global fit of neutrino oscillation data by the Valencia group. And we use the expression of the lepton mixing in terms of the mixing angles and the masses of neutrinos in order to be able to extract the constraints that we get. And these are our results. Here I show you the compatibility regions in the plane of theta 2, 3, and delta. I showed the results for normal ordering and also for inverted ordering and for the 3 possible constraints that we get. Decoupled electron, mu1, and tau. Notice that I only show you here 5 of the possible 6 cases, because the case of inverted ordering and decoupled electron leads to vanishing neutrino-less double beta decay, and we know that this is incompatible with inverted ordering. Now, looking at these 3 cases here, as you can see, the model allowed regions coincide with the experimental ones. But on the other hand, for these 2 cases here, the model will choose a particular octant for theta 2, 3. So once we get a better measurement of this angle, we will be able to exclude one of these cases. Now, moving on to the more interesting constraints on lightest neutrino mass. As you can see, for the case of decoupled electron and normal ordering, our model establishes both an upper and a lower limit on the lightest neutrino mass, and these 2 limits are still well below the current limits from Catherine, here in dotted line, and also the limits from Planck, the most conservative limit and the less conservative one. In these 3 cases, as you can see, the model gives us a lower bound on the lightest neutrino mass, and this bound is now currently being probed by cosmology. Finally, for the case of decoupled mu1 and inverted ordering, the model still allows for lightest neutrino mass that are smaller. Moving on to the constraints on neutrino-less double beta decay. Here I show you the results in the plane of the lightest neutrino mass and m beta beta. M beta beta corresponds to the effective mass, which expressions I show here. As you can see, for normal ordering and for inverted ordering as a function of the mixing angles and also the masses. These plots show a very interesting thing about our model, which is even though we have considered a very simple discrete symmetry, we still get some very constraining lower bounds on m beta beta. In particular, in the cases of normal ordering and decoupled mu1 and normal ordering and decoupled tau. And almost all the region for normal ordering is already excluded by current limits from neutrino-less double beta decay experiments. And surely future updates on these experiments will be able to probe the entirety of the region. For the case of inverted ordering, we still have to wait a little bit longer in order to be able to test our model. Finally, for the case of normal ordering and decoupled electron, we have a prediction of vanishing neutrino-less double beta decay, so that case is still allowed by data. So to conclude, we propose a very simple Scotto-seesaw model where neutrino masses, dark matter stability, and also spontaneous CP violation are commutated using this single Z8 symmetry. This symmetry will be broken down by the VEV of our new scalar singlet. And this will be actually the unique source for CP violation in our model. This CP violation will be successfully transmitted to the leptonic sector via the couplings of sigma to our neutral fermions. And also this symmetry will be the source of constraints, low energy constraints, which we tested against data. And we concluded that for normal ordering, the predicted ranges on M-Litus will be fully tested by near future neutronal stable beta decay experiments. While for inverted ordering, we still need a better determination of the Dirac phase, and also wait for improvement in neutronal stable beta decay experiments. That is all. Thank you for your attention, and I'm happy to answer to any questions that you may have.
Many thanks for your talk. I'm sure we are having questions.
A quick question, please.
Maybe wait a second for the mic.
Do you have
Okay. We have a remote question. Let's start with the remote one first.
I was wondering if there's a domain wall problem because Z8 is broken to Z2.
There's not a problem in our model because actually we have a softly broken symmetry. Let me just show you the potential. Can I change the slides, please? Okay. So as you can see, we have a term which is sigma squared. So this softly breaks the symmetry, so we will not have that problem of domain wall formation.
So you don't have an exact Z8 symmetry, just softly broken Z8.
Yes, yes, exactly.
Yes, I missed the scale at which the CP violation happens. It's vacuum value of one of the fields. What scale does that happen at?
Certainly below the electrolytic scale, but we don't have a fixed scale for.
Below the electrolytic?
No,
above.
Sorry, above the electrolytic scale, yes.
But no particular value.
No.
Thank you.
We would have time for one more question. Otherwise, let's thank the speaker again. And I'm asking the final speaker of the session to present on non-unitarity mixing matrices in neutrino and vector-like quark models.
Olá, ouve-se bem? Ouve-se bem? I sent by email, yes. It's not bad. It was this morning. Yes. Talk to Pedro Emir. Yeah, that's it. Do I have, okay. Can you put full screen?
Okay, great. Please go ahead.
Hi, I'm Pedro, and first I would like to thank the organizers and my supervisors for the opportunity to be here. This talk is based in work done in collaboration with all these people. Actually, most of them are here. You should meet them because they are very nice. So today I want to try to convince you that there is a simple and exact parameterization usable in models that have non-unitary mixing matrices. You can ask why. So when dealing with deviations from unitarity of the mixing matrix, in the literature, we usually found approximations, and this is fine because often they simplify the problem, and if used when the approximation is valid, the result should be reasonable. But sometimes we want to study a region where these approximations fail, or to perform a general scan of the parameter space of a given model. So as an example, I will apply this. I will start constructing this parameterization, and as an example, I will use vector-like quarks and neutrinos. So without symmetries, we will just write the most general Lagrangian of the standard model, adding NR right-handed neutrinos and NU up vector-like quarks, or ND down vector-like quarks. This NQ can be NU, so Q can be U or D depending on the. So this is the mass Lagrangian that we obtain, and this is well known, so I'll just move on. So the first thing we should do when we have these mass matrices is to diagonalize them. And the first step is to label things. So we have a calligraphic V that is a 3 plus n times 3 plus n unitary matrix. And we will label the top rectangle A. And A is a 3 times 3 plus n. And the bottom rectangle as B. And B is a n times 3 plus n matrix. And these rectangles are only unitary on the right, but that's a detail. Okay, moving on. After this labeling, we use these diagonalization equations, and we obtain these equations for the mass matrix. This is still not very helpful, but this is just the starting point. We already see that we have a zero that will restrict severely and will help us in the future. The zero comes from gauge invariance in neutrino type 1 model. So moving on, we write the Lagrangian for the charge currents, and the matrix that controls these charge currents is what I call V, and what I will refer as a generalized mixing matrix, and the mixing matrix is just the 3 times 3 part. So V should be a rectangular matrix. And in the case of, I forgot to tell you, the top part is always related to vector-like quarks. This part below is always related to neutrinos. In the left, always vector-like quarks. In the right, always neutrinos. So this has a logic. Okay, so in neutrinos, V is just A, and in vector-like quarks, if we have up and downs, it's given by this. For the neutral interactions, we see that. By the way, note the similarities between two things, because we are adding vector-like fermions. Neutrinos are vector-like fermions in a way. So things should mathematically be similar, and they are. And note that the matrix that controls the neutral interactions is given by this F, which is basically given by the deviations from unitarity of this A. And we already see that flavor-changing neutral couplings are given by the off-diagonal term of F, which means that flavor-changing neutral couplings are proportional to the deviations from unitarity, which should be small, so everything makes sense. Okay, this is the next step. We will now discover what A and B are. So we proved in one of our papers that we can write a 3 plus n times 3 plus n unitary matrix calligraphic V only using 3 matrices, K, K bar, and X. And these are completely general. So they are not unitary, they are not Hermitian, they are nothing yet, okay? The only assumption we use is that K and K bar are non-singular, which in physics is reasonable. So we now know that the top rectangle, A, is given by K and Kx dagger, and the bottom rectangle is given by this. B is not that important, because it doesn't appear in the Lagrange. So again, coming back here, we now know what A and B are. So we substitute things, and we obtain this. In the neutrino sector, as I told you, we have this zero that severely constrains things. So we get an equation for X for free. which is given by this. And this OC is a complex orthogonal matrix, which this might ring a bell for some people because of the Casas-Ibarra parameterization. And if you see, if this is a general and exact parameterization, this in some given space, it should coincide with the Casas-Ibarra parameterization. And it's the case because M has an X dagger here, so M will have a OC dagger, which plays the role of the complex orthogonal matrix we can find in the Casas-Ibarra. And for the vector-like quark case, things are not so easy, but we can go to a weak basis in general, where one of these, actually these two, can be zero. And here I chose the weak basis where the small m bar is zero. And in that basis, we find an equation for XL and XR. So we now have equations for X. And with some algebra and using that theorem that the general matrix can be written as a unitary matrix times an Hermitian matrix, we realize that K is given by this, and K bar, I'll just talk about K because it's the important one. So where UK is a unitary matrix, and this part here is an Hermitian matrix. And we see here that when X is 0, K is unitary. This is the standard model case. So we know now that K, the PMNS, the mixing matrix in this case, is given by K. And in the case of the vector-like quarks is given by this. So it's the same structure, exactly the same structure. A unitary matrix times an Hermitian matrix. We can also have formulas for Fs, the ones that control flavor-changing neutral couplings. And we see again that the off-diagonal terms are proportional to the deviations from unitarity. Okay, so putting all together, we have a formula, a complete formula for the calligraphic V. And there are some works prior to our one that had a similar structure, but or either they used some kind of approximation at some point, or it ended up being a special case of this one that is more general. I will now tell you like the procedure to use this. So we can do it in the two directions. We can go from here to here and from here to here. We can start just with the light I will just talk about neutrinos because it's the same thing here. We can start with the light masses, D, with the heavy masses, the unitary part of the mixing matrix, and then the OC and the PQ. I forgot about this, sorry. So PQ is the matrix that is in the vector-like quarks, X, and since we don't have this 0, things are a bit more complicated, and PQ is just a general matrix. So when adding vector-like quarks, we add a lot of new parameters. In the neutrino case, it's a complex orthogonal, so more restricted. So yes, we can start just with the masses, the unitary part of the mixing matrix, the OC or the PQ. We calculate X, and then we can calculate the mass matrices, V and F, and everything is exact at 3 level. Or we can do the opposite way. This is more useful when we have symmetries, so we want to start with the mass matrices, and we can just do this. But even for numerical calculations, it's always easier to have formulas that are exact, at least at 3 level. So things that we should worry about. Radiative corrections on the light neutrino masses. Although we have everything exact at 3 level, when deviations from unitarity are sizable, we have to care about radiative corrections on the light neutrino. The other thing is perturbativity. So there is kind of, even when we are out of the seesaw approximation, there is kind of a seesaw here. And this seesaw is between the deviations from unitarity and the heavy mass. And this can easily be seen here. So X is basically parameterizes the deviations from unitarity, and D is the heavy mass. So if one goes up, the other must go down. Otherwise, we have Yukawa complex of order 10,000. So it's kind of, there's always kind of a seesaw between two things in this framework. Yeah, okay. So the usefulness of all of this is that we have exact formulas at tree level. It's easy to implement, numerical, and is in principle extendable to every model that has non-unitary mixing matrices, like inverse seesaw, linear seesaw, things with vector-like fermions in general, whatever. So you can ask, has this been used? Yes. So the first time we used this was in this paper. And the point of this paper was to see if it was possible to match the upper bounds, the experimentally allowed upper bounds on deviations from unitarity. And we did this considering a spectra of heavy neutrinos all around the TeV scale. And the answer is yes. It's not like that thing that when the name of the paper is a question, the answer is always no. So the answer is yes. Then I had, after reading some things about the short baseline anomaly, and that one possible solution would be an electron volt sterile neutrino, I had the idea of, okay, we had all this machinery that is exact, so we can construct a type 1 seesaw with sizable deviations from unitarity. Because of that seesaw thing, if we have like a mass, a heavy mass of 1 electron volt, it goes down, so the deviations from unitarity can go up. And the only way to treat this is with an exacting, because the light sector doesn't decouple from the heavy sector. So after reading some things about the short baseline anomaly, I realized we could construct a model with electron volt neutrinos that would make sense. So we would have order 1 Yukawa couplings, and everything would make sense. So we ended up realizing that due to radiative corrections, only these 3 types are good, because we have to introduce a electron lepton number like symmetry U1 and softly broke it, and these are the only 3 spectra that we found. So with 2 electron volt and a gut, and these are masses, yes. The other spectra was with 1 heavy neutrino with an electron volt mass, another with the key EV and another gut, and another spectra with 1 electron volt heavy neutrino and 2 TeV that are quasi-degenerate. And we also studied the effects on CPS symmetries that are measurable in a long baseline experiment. We also did this paper recently where we explained the CKM unitarity problem by adding a vector-like quark, an up vector-like quark to the standard model. And we started doing it with this parameterization, but we ended up not using it because we are adding just 1. And we can just use the parameterization of the PDG, but for a 4x4 mixing matrix. And things are tractable. But more than 1, things start to get shaky. We are also, the first time we will introduce this on vector-like quarks will be in a review that we are working in collaboration with Nishi and Chershia. So we hope this to be available soonish. That's it. I don't have conclusions because these are basically the conclusions, the usefulness of the parameterization. So thank you.
Many thanks. I'm sure we're having questions. So the first one here.
This is more to the model than to this precise topic. Having vector-like fermions, massive ones, mixed with the usual ones, you usually indeed assume it's mixing with the heavier ordinary fermions. And that means that it's really a basis-dependent statement. And furthermore, if I understand, you were looking here at the mixing in the, was it in the up sector, right? Up or down sector?
No, we considered in general adding up vector likes or down vector likes at the same time.
And both mixing to the standard quarks?
Yes, yes. Just it was completely general. This was just like a toy example of how to work with the parameterization without any extra symmetries.
Agreed. But now the problem for me is how to enforce that coupling to the heavy.
Well, in general, it exists.
And
you have to enforce something such that the coupling doesn't exist, right?
Yeah, but that means you choose a basis, and the relation.
There's only one
between
physical
particles
basis, no?
determined by the mass. So let me just finish this one. Well, in a way, I think it would be much more natural if you're mixing with the heavy quarks. Heavy quarks would bring some of the mass. And this is not the case.
Yes, I agree.
It's not the case in SU2 cross U1 models, but it would be the case in left-right models, for example.
Yes, but you can add symmetries and you can still use this. And you would have things like that, where the masses come relatively or from interactions with the heavy states. Yeah, I think Gustavo has some papers where things are like that. At tree level, only the top has a mass, and things show up because of the interactions with the vector-like quarks. Yeah.
We have further questions. That doesn't seem to be the case. Then let's thank all the speakers of the session again. And that is we're closing the session, and we reconvene in about 20 minutes for the second afternoon session.